The warm-up question for today asks you to draw a free body diagram for a soccer ball just after it's kicked rightward, so where it's at the position shown. So it's just left his foot. It's at that spot. It says to assume no air resistance. And when you look at this question in My Open Math, same picture, you have a spot to draw that free body diagram right here. So let me ask you before I draw anything, what force or forces would be acting on that ball at that position? Gravity. Is he still kicking it? No. He did apply a force to make it move, but you would not draw an applied force at that position. As soon as it's left his foot, the only force acting on that object is gravity, which makes this an object in free fall. Okay, so we would not draw that applied force. I wanted to just go over that because I figured that some of you might say that, and I expected it. It's okay, but I just wanted to make sure to cover it. But that's the only force acting on this object because it says there's no air resistance. That would be the only other possibility, unless, of course, there was something continually applying a force if he was somehow continually kicking the ball, which is not happening. So it's just that one. It's just gravity. The net force is downward. Even though the ball's moving up and to the right, the net force is down because the only force acting on it is the force of gravity. Okay, so I don't want you to mix up velocity and acceleration, or in this case net force, which is producing that acceleration. You need to make sure you understand the difference between the fact that it's moving in one direction but accelerating in a different direction. Okay, so those are not the same thing, velocity and acceleration, and that's what we focused on in the first 2 units of this year. But I wanted to kind of go back over it and tie it all into forces. So you should be able to answer this warm-up question and get your free body diagram kind of filled out on there. We are going to take some notes today over Newton's first law in your homework assignment tonight, and you should hopefully have some time to work on it in the class period today, is 401.1 inertia problem set. So let's go ahead and get into the notes. And what is inertia? Okay, well, Newton's first law is also called the law of inertia, so we need to know what inertia means. Inertia can be defined as the resistance an object has to a change in its state of motion. A state of motion is just referring to its velocity, its movement, which way it's going, how fast it's going. Okay, and so inertia is the tendency of that object to maintain that velocity. Keep going in the same direction with the same speed. Okay, it's resistance to changes to that motion, and so you can call it resistance to acceleration as well. Inertia is directly related to mass. Okay, I put 2 pictures up here and I labeled them A and B, and one of them is a box filled with a bunch of books and the other one's just an empty box, and it says you can ask yourself which object would be harder for me to accelerate. Okay, just looking at those 2 pictures, which one would be harder for you to accelerate? A. Okay, it is directly related to mass. Its resistance to acceleration is directly related to its mass. Its inertia is directly related to its mass. A has more inertia because A has more mass and therefore has a greater tendency to resist acceleration. It's harder to make it accelerate, to change its state of motion. Okay, so again, inertia, the resistance an object has to a change in its state of motion. Changes in state of motion would be changes in velocity, which means that this is also, or you could summarize it as resistance to acceleration. Okay, so again, same thing as on my screen. This is directly related to an object's mass. Therefore, you should be able to answer questions like this. Which has more inertia, a bowling ball or a person? Person, unless you're talking about like an infant, maybe they're the same. Okay, but yes, a person would have more inertia because a person has more mass. Okay, same thing, your desk or your chair? Your desk. Okay, and again, you know because of the masses of those objects. So if I ask you a question like that, which has more inertia, you're going to base it solely on the mass of that object, not how fast it's moving or anything else, but just its mass is going to determine how much inertia that object has. Okay, so again, Newton's first law is also called the law of inertia, and it states, and you've probably heard this before, an object in motion will remain in motion with a constant velocity, And an object at rest will remain at rest unless acted on by an outside unbalanced force. Okay, so you've probably heard something that sounds like that before this class. I know they do it in junior high science as well. Okay, and so it brings in a term that we just looked at in the last unit, unbalanced force. Okay, and so we've talked about already balanced and unbalanced forces, but just to kind of review a little bit, in order for us to better understand what this law is saying, we need to make sure we understand what it means for forces to be balanced or for forces to be unbalanced. Okay, and again, that is part of what was in our last test, and I think you guys probably had that down based on how y'all did on that test yesterday. Okay, but again, an object in motion will remain in motion, an object at rest will remain at rest unless acted on by an outside unbalanced force. So again, tendency to resist changes in state of motion. If I resist a change in my state of motion, I'm going to keep moving with a constant velocity, or I'm going to keep being still. Okay, again, that's inertia. That's why it's called the law of inertia. Okay, so back to these real quick to very quickly review, and you can jot it down if you need to, but balanced forces, as a reminder, are equal in size and opposite in direction. When forces are balanced, there is no change in motion, and we say that the net force is zero. So I have an example up here of a free body diagram of a book, and this book might be sitting on a table or the floor. We don't really know. All I know is that the forces on it are balanced. It has weight. It has Fg, the force of the Earth's gravitational field pulling on it. And it has Fn, that support force from the surface that it's resting on. And those two forces are equal and opposite, and therefore the net force is zero. Okay? You could draw this exact same free body diagram for yourself right now sitting in your chair, or for your computer sitting on your desktop. It would look just like that. Okay, but those forces are balanced. They're equal in size and opposite in direction. And when the forces are balanced, there's no change in the state of motion. Again, that's what Newton's first law said that we just looked at a second ago. It said that those objects would remain in motion at constant velocity or remain at rest unless there's an unbalanced force, which means when they're balanced, those other things are true. But when they're unbalanced, okay, that's when you have a change in your state of motion. Again, we talked about unbalanced forces already, but an unbalanced force, or rather unbalanced forces, exist on a system when the net force is not equal to zero. The forces don't cancel out, and you get a resultant net force, and that net force is responsible for acceleration, and that's Newton's second law. Okay, we looked at that all last unit, how that net force will produce an acceleration of that, whatever that mass is, F net equals ma. Okay, so if you have a net force, it is responsible for the acceleration of your system. The diagram I drew up here might be that same book being pulled by a rope across a table where there's friction. Okay, and I say rope because I see tension up there. Okay, so if you had tied your lanyard or a rope to a book, I don't know why you do that, but whatever, maybe you're pulling it by the bookmark. Sometimes they have them built in. Okay, but you can see the forces up here are not canceling out, at least not in the horizontal direction, and therefore there are unbalanced forces in the horizontal direction acting on this book. And it would therefore accelerate to the right. Doesn't mean it's moving to the right necessarily, although it does in this case because friction's labeled to the left. All right, so net force again must be calculated separately for the horizontal and vertical directions. This part is a review, so this should all sound familiar. But when we look at diagrams like the one we just looked at and we calculate net force, we have to calculate it separately in the vertical direction than we do in the horizontal direction. If the forces are in opposite direction, they will cancel out in part or in total. If they're exactly the same magnitude, they'll completely cancel each other out. If a net force exists in both horizontal and vertical directions, then a resultant net force is drawn at an angle and calculated using Pythagorean theorem or trigonometric functions. I told y'all last unit that we weren't doing that yet. We are doing it this unit, but not today. Okay, so you are going to have to, we're going to be looking at that. So just keep that in the back of your mind, or maybe just do a little review over the weekend of sine, cosine, and tangent, or SOHCAHTOA, that acronym that they teach you in your math class. All right, so I'm going to show you this quick video clip about inertia and car crashes, the tendency of objects to remain in motion unless there's an unbalanced force.
Newton's first law of inertia states that an object stays in motion with the same speed and direction unless acted on by an external force. Normally, a car and its occupants move around at the same speed, but when an external force is applied to the car, in this case by the crash test block. The occupants continue to move forward at the same speed until a force is applied to them. This resistance to a change in motion is called inertia, and it applies even when the velocity is zero. It's this property that enables people to do things like this. The china on the table stays pretty much at rest, even when the tablecloth's pulled from under it. That's because there's not enough sideways frictional force to overcome the china's inertia and get it to move. Back to the crash test. Because they're not wearing seatbelts, inertia means the occupants of this car continue travelling forwards until the windscreen applies the force to stop them.
Let's look at the inertia here. You can see the vehicle coming forward, it's stopping, but the occupants carry on because there's nothing stopping them carry on. That's the basic Newton's law here. So you can see the occupants, because they're unrestrained, the driver has hit the steering wheel and the whole steering column is crushed around him. You can see he's partially ejected and will be severely injured. The poor passenger, even though he was in the back of the car, protected by the front seat, because he's not restrained, he goes through the front seat and he's gone through the windshield, and you can see his head still sticking out there.
Of course, in real life, you get a lot less time to regret not doing up your seatbelt. Newton's first law gives us the idea that in a car crash, things keep going until something stops them. First used in the 1950s, seatbelts provide an external force that counteracts the passenger's inertia, bringing them to a halt in a more controlled way. But they're just one of the ways car designers reduce the forces on the occupants in the event of a crash. And every car designer also needs to understand the principle behind Newton's second law of motion.
Okay, so just a very real world tie-in with this is wear a seatbelt, okay, because you are an object in motion and you will remain in motion at however fast you were driving, 60 miles an hour, 75, I don't know if you're on 99, then you're going to remain in motion until something stops you, and hopefully that's the seatbelt and not the windshield, okay, or something else. But inertia is easier to see in the absence of outside forces, because if we, look and think about just real world things, and if I try to, kick a ball across this room, okay, well, maybe not this room because that's too big, but if I were outside, like on the soccer field, and I kick a ball, okay, it's not going to go forever. But that's what Newton's first law says, okay, object in motion will remain in motion. Okay, unless there's an unbalanced force, and that's the problem. It's really hard for us to get rid of all of those unbalanced, those outside forces that could cause that ball to slow down. We can't really get rid of friction, okay, on Earth. We're going to have that there. We don't really have truly frictionless surfaces, but in space you can see it a lot easier, okay, because in space we don't have those other forces, or at least not the same ones. They're not as obvious with these objects that are moving in an environment that is basically a void, where there is no air, so there's no air resistance, there's no friction. The only forces that you would have if you're anywhere near a planetary body is, of course, gravity. Okay, but in orbit around the Earth, astronauts know that once one starts to float away, there's no way back unless something or some force opposes the motion. Okay, again, force isn't necessary to maintain motion, but forces like friction can stop motion. So it is a common misconception is that you have to keep applying a force to keep something moving. Okay, and that is only true, of course, if there is some kind of outside unbalanced force that would be slowing it down. Here's a question that should look kind of familiar because I think we gave you the same one in the last section, but it says, a spaceship in frictionless deep space fires its engines for 3 seconds, which describes its motion at the end of the 3 seconds when the engines are turned off. So I just put some example numbers up there for the first 3 seconds. And I am showing that when it fires its engines, of course, that would be an unbalanced force. Okay, there's a force acting on it, a net force. Okay, and that net force is going to produce acceleration. Again, we talked about this last unit. So I have acceleration here. I have a change in my velocity. Specifically, I have a change in my velocity of 20 meters per second each second. Okay, so you can see acceleration up on my screen right now in that data table. Okay, but what's going to happen when the engines get turned off? If that force is removed, what happens to the spaceship?
It keeps going.
Yeah, it keeps going at a constant speed. Again, that net force from the engine causes acceleration, but the spaceship doesn't stop just because the engine's turned off. When the engines are turned off, all that means is I have zero net force now. And it means I have zero acceleration, but it doesn't mean I have zero velocity. I was already moving 60 meters per second. Okay, and if I'm already moving 60 meters per second and I have no more net force, now I have that inertia. I'm going to continue moving 60 meters per second at a constant velocity based on those numbers. Okay, so again, just because I turn off the engines, I don't stop moving. I'm going to keep moving at whatever speed I was already going, in this case 60 meters per second, now that I have a net force of zero and no acceleration. So again, when the engines are turned off, there are no longer any forces acting on the spaceship. The net force is zero, so it will travel at a constant speed. This is Newton's first law. An object in motion will remain in motion unless acted on by an unbalanced force. And you can prove it mathematically with the second law equation. Of course, his laws are all tied together. And we already did those mathematical proofs. Okay, but I could draw a free body diagram for each portion of its motion. Okay, in that first part where I have the engines turned on, maybe the engines are applying a force to the right. That's what I did on my screen. Okay, but whenever the engines are cut off, what forces are acting on it? None, right? We're in deep space. You wouldn't be able to draw anything. There aren't any forces acting on it there. That's why you have zero net force, you have zero acceleration, you have constant velocity. Okay, so you can see that in the data table as well. Okay, how is the spaceship moving when there's no forces acting on it? Okay, and again, it can still be moving even though there are no forces acting on it. It was already moving. Okay, so it has inertia. It will continue moving until forces stop it. Forces are not required to keep objects moving. Okay, again, that's a very common misconception. Forces don't keep objects moving. Newton's first law of motion declares that a force is not needed to keep an object in motion. Again, the problem is that whenever we try this on Earth, on surfaces where friction exists, like if you tried this right now, push a book or your calculator, try to slide it across your table, of course it's going to come to a stop. We already know that. Okay, and so that's where the misconception comes from. People think if the spaceship is in deep space that you have to keep the engines going to keep it moving, and you don't. It will keep going all by itself because there aren't other forces out there to slow it down. So again, whenever you try this here, that book or a calculator, whatever it is that was moving on your tabletop, does not come to a rest position because you stopped pushing it. It's not because of the absence of a force, but rather because of the presence of one. It's because of the force of friction that brings that book or whatever that object is to rest. And again, we see that in our daily lives. Okay, so if you wanted to, you could draw the free body diagram to illustrate the forces acting on a book, moving to the right across a desk and coming to a stop. And we would have, of course, friction, gravity, and normal force. We've done these types of diagrams in the last unit. Okay, our force of friction would be to the left in this example. Our Fg would be down, Fm would be up. And of course, in this example, I said moving to the right and coming to a stop, so the hand wouldn't be on it anymore. So it's like after it's been pushed. But I have my friction, I have Fg, I have Fn. I don't have any forward force, and that's okay. It can still be moving forward. Okay, it's coming to a stop. In fact, it is moving forward. It's coming to a stop, though. You're not going to see a force vector there for something that's already in motion, like the ball in the warm-up that's already been kicked. You don't get to add that force there unless it's continually being added. Of course, if the hand was actually on the book continuing to push it forward, yes, you would draw an applied force there. Okay. Again, acceleration means unbalanced forces, and that's what Newton's second law was all about. A net force causes acceleration. The acceleration of the object depends on the net force acting on the object and the mass of the object. Should already know all of that stuff, but you're welcome to write it down again if you need to. These should look familiar. We don't get away from this just yet. Again, choose one, more than one, or none at all. Which of these could be at rest? A, B, C, D. Which ones could be at rest? You're going to see these questions again in this unit. A could be at rest. C could be at rest. Okay, again, the ones that have zero net force, the ones where the force is canceled, could be at rest. They could also be the ones at constant velocity. Same answer. Okay, we don't know whether or not they are moving or which way they are moving unless we have more information. And that's the answer to the last one. Which direction is A moving? I have no idea, and neither do you. You cannot tell. We just know that it's not accelerating. We don't even know if it's moving. Okay, but if it is, it could be moving up, down, left, right. I have no clue. Okay, I would need some more information given to me. So again, an object at rest stays at rest. An object in motion stays in motion with the same speed and in the same direction. That's a longer way of saying with the same velocity. Okay, unless acted on by an unbalanced force. So which ones show an unbalanced force? Well, of course, that's going to be the ones where the forces don't cancel. That's B and D. And when there is an unbalanced force, we of course have acceleration. They have changes in their state of motion. Okay, so these two would have acceleration. They would change their state of motion. Again, that's this part right here. Unless acted on by an unbalanced force, there is our unbalanced force, and that means we are no longer maintaining our velocity, whatever it is. Object at rest won't stay at rest anymore. An object in motion might stay in motion, but it might be speeding up or slowing down. Okay, and because of the unbalanced force. All right, so again, a lot of that was a little bit of a review because we kind of talked about Newton's first law already in the last unit without talking about Newton's first law. So it should have looked somewhat familiar. Your assignment today is 401.1 inertia and FBD problem set. It is due tonight by 11:59 p.m., but you should have no problem finishing it in the next 20 minutes that you have in class. So if you want to get that opened up and work through it, go ahead and do that. Obviously, if you have questions as you are working, please let me know. But I'm going to let you guys get to work.